Started on. Thank you all for joining. My name is Sydney Forrester. I work at Lawrence Berkeley National Lab, and I'm joined by my colleagues Eric and Chris, who are also co-authors on this report, along with Galen Barbos, our PI, who couldn't make it today. We're here presenting on this open access journal article that came out earlier this month in Nature Communications, and the link will be posted at the end of this presentation. We'll have a link to that, and we'll also have a link to some other work by our department. But we also want to thank the Department of Energy's Solar Energy Technologies Office for funding this work and for also all of their support. And let's get started. So just some housekeeping. This is being recorded. The presentation, both in PowerPoint form and in video form, will be posted to the link that I will share at the end, and it'll be updated after this presentation. The Q&A is being managed by Eric, so please feel free throughout the presentation to put questions in the Q&A section of Zoom, and we'll get to them at the end of the presentation. We should have around 20 or 25 minutes to go over those at the end. Great. So this work was going on for a while, and again, it was just published earlier this month. It is on the impact of residential rooftop solar on energy burden for households across the U.S. So just quickly getting into the outline of what we'll be going over today. So first, I want to go over some background and motivation for this work, and also data and methods that we used, and I guess also more specifically, some limitations of this work as well and assumptions that we made. The majority of this presentation will go over results that, again, are pretty much drawing from the figures from the actual article that will be linked, and then finally, some key takeaways. So I actually am starting with the key takeaways slide that will show up later on, just to go over a little bit of a primer, a hint of what's to come. But we essentially looked at 500,000 households across the US. We really wanted to leverage empirical household level data. We did have to combine this with some modeled data at the household level or some aggregated data at times, but what we really want to do was to combine the bill impacts and incentives of solar adoption with the actual costs of adoption as well. So comparing sort of the costs and the benefits financially to the households to come up with sort of a net financial impact to the household. So when we did that, what we found was that we had essentially reduced energy burden due to solar adoption across the majority of these adopters in the US. So that was about 3/4 of adopters. And again, that is taking into account the cost of paying back the system. And these were also adopters over the past 10 years. So when we look at the results, we slice and dice them a few different ways through a few different groups that we'll talk about in the results section. But we did this by year of adoption, by income level, by ownership type, primary heating fuel, and region in the US. So a large focus is on the income group breakdown, just because, energy affordability especially matters for more income limited customers. So we're focusing on those that we define at 80% of area median income or less as low income, and then moderate income, which is 80 to 120% of AMI. And we really focused a lot on those groups. And what we found was that the energy burden reduction on a percentage point basis especially was more pronounced for low and moderate income adopters. Even so, when just focusing on that 80% of AMI or less, what we found was that the percentage point reduction was very large for this group. However, high burdens did persist for roughly half of those adopters. So this bullet, I think, is really important. it emphasizes two things. One is that solar was very effective at reducing energy burden and reducing the sort of incidence of high and severe energy burden in this income group. However, just because it started at such a high level, that reduction got to a level that was still a little bit maybe on the margins of being too high for some households. So in these cases, it's really important to think of rooftop solar as a complementary strategy along with other interventions such as weatherization and bill assistance that have been around for, 4 decades essentially. So one of the groups that we sliced and diced by that sort of produced large variation was by region. So I'll get into this a lot more in the slide that is specific to that grouping. But what we essentially found was that in the West, this is, again, the study period was 2021, which was the year of the most recent data across all sets. This is like one big caveat I think that's very important to note, is that in 2021, a lot of the conversation about net metering successors that's happening also, especially in the West. I'll show you next slide, but or in a couple slides, but the residential rooftop solar market is predominated by California. And obviously in California right now, there's a lot of conversation about residential rooftop solar compensation. So that is just one caveat here, is that the study period is in 2021. And so net metering was in effect in, the majority of our sample. So in the West, high electricity prices and good solar resource led to the greatest burden reduction. And in the Northeast, we saw a big percentage point change, so a big reduction in energy burden. However, because the Northeast is a colder climate, there's larger number of heating degree days, and then also larger non-electric burden. So not only natural gas, but things like propane and heating oil. So these burdens kind of, the whole energy burden, the ability of solar to impact the entire energy burden was a little bit limited because solar obviously can only impact the electricity portion of that entire calculation. The Midwest saw burn reduction, but at a lower level than the West or Northeast. I will also say that you'll see in the slide that the starting point for the Midwest is also a little bit lower than the other regions. Not as low as the South, but it is fairly low compared to the Northeast and West. And then the one increase, so across all of the groups in all of the groupings that we looked at, the only increase in energy burden across these averages was in the South. And this is largely due to low electricity prices that mute the impact of savings because of, limited bill reduction potential. So at this point, I think a lot of people are familiar with energy burden. However, there are some variations, sort of study to study, on the specific definition. When we talk about energy burden in this paper, we're not only talking about electricity costs, but also, again, natural gas costs, but even off-bill things, like off-utility things like fuel, oil, and propane costs to heat your home. And then when we talk about solar's impact on energy costs, again, we take into account the bill savings, which is pretty standard. But we also take into account the costs. So in a case where there's some sort of on-bill recovery or on-bill financing, you will see sort of the net impact of solar adoption on the bill, so both the cost and the bill savings. But in cases where you're paying for it off of your bill via a lease or a loan, those might not always be included in every single energy burden calculation. So it's important to note that for our study, we do include the costs of solar adoption, even if it is off bill. So here we also state that a high energy burden is defined at or above 6%, and then a severe energy burden is at or above 10%, and that's consistent with literature and other definitions in the space. So first off, some motivation for the research question and why we focused on energy burden as a metric in general. So recently, equity as a whole, an energy burden as a metric more specifically is becoming more common in programmatic goals and also in programmatic targets and evaluations, as well as in sort of legislation, executive goals, et cetera. So an example of that could be Justice 40 at the federal level, which does target decreasing energy burden for disadvantaged communities, for homes in disadvantaged communities as a goal. Also, I guess more specifically, is a month ago, the Solar for All awards were awarded, and that is likely to sort of trickle down into sort of using solar to reduce energy burden and increase energy affordability at the state level or even more local. So there is a bit more of a prevalence of solar being used with the primary goal of decreasing energy burden or increasing energy affordability in homes. And that historically has mostly been the focus of things like weatherization and bill assistance. So solar is kind of just now becoming more common in that space. Also, because of that, a lot of the studies in the area have focused on weatherization and bill assistance, and a bit only more recently on solar. And there are obviously, with energy burn specifically, challenges with data access and availability, just because if you think about that equation, you have the cost of energy and you have the income of the household. And the cost of energy can be difficult because that might be something that only the household knows or the utility might have access to, so it can be hard to get. And then the income of the home can be tricky just because, again, that could be more sensitive information and hard to obtain at the household level. So in a lot of cases, these studies rely on aggregated data or some assumptions. So you'll see things like energy burden at the tract level or something like that. Another thing is that to fill in the blanks, and this is also something that we had to do, but you have to sort of rely on model data in some cases. So I will say that some studies rely primarily or exclusively on modeled data, and we were able to sort of mostly leverage our empirical data and sort of fit in modeled data where absolutely necessary. And then even then, whenever we did that, we did it at a super granular, geographically granular level. That's not to say that there aren't any empirical analyses on this topic. There are, but usually these are sort of more in the realm of program evaluation. So it is specifically focused on a specific program that might be in one region. So the final thing here is just that analyses don't always account for the net financial impacts on the household, like I mentioned earlier. So really taking into account the cost of adoption is very important when looking at investment that's as significant as rooftop solar. So our analysis, again, it does sort of fill a lot of these gaps, and I'll go over some again of the caveats here, but we really do aim to fill these gaps by making it household specific, getting geographic coverage across the sort of entire residential rooftop market in the US, or as close to it as possible. And we do, again, leverage empirical data at that household level, and really only fill in the blanks that are necessary with some of the other model data. So to get this big data set where we will share the results from, we had to do quite a few different steps. So the first step was really just getting all of our empirical household level data to agree with one another. So some of you might be familiar with our group's annual report, Tracking the Sun. So this is a very large report released annually that gets into empirical cost and installation data, so all the solar specs of rooftop solar in the US. So this is empirical data on essentially the size, the cost, the incentives, whether or not it's host-owned or third-party owned, and all of that. So our annual solar demographics report then goes one step further by taking the sort of address level stuff, and we purchase Experian estimates for income and demographic information. So these are sort of like best guesses at income by Experian. So again, this income specifically is not empirical, but it is at the household level. So we take that, and then we also have empirical data on the actual structure of the residence. So we know the size, we know the heating fuel type, and we also know other things that have to do with the building itself. So what we do is we take that, and then in step 2, in order to get the solar production and the load both at an hourly level, we use the NREL system advisor model, and we come up with a capacity factor for each county, depending on where the household is located. And then with that, again, we have the empirical size information, so we can estimate, again, like an hourly curve for the generation profile of the solar system. We also have the age of the solar system, so we can sort of decrease the production in ways that make sense with aging. For the load, what we do is we take all of the empirical building data that we have, and we find sort of the closest match with NREL's res stock, and we match it based on a bunch of different similarities with the buildings. And then what we do is they have a set of end use load profiles and usage of different electricity and fuel types. And we calibrate that by other empirical data that we have, like the actual size of the building, and the sort of the solar system, the empirical solar system size. So we basically match it with the model data and then calibrate it and use those as the hourly load. For the costs, we use, for all non-electric stuff, we use US EIA data. So that is specific to the fuel type, the state or region, and then the month or year, depending on how granular we can get. And then for the electricity tariff, this is both an assumption that we made, but also like just an indication of like how much we tried to get really as close as possible to the actual thing. We used an API to collect actual tariffs, basically for each customer. So how we did that was we took each customer's zip code. We found the most likely rate that they would be on, so the highest probability rate for a residential customer without solar and then with solar. So in some cases, they stay on the same rate when they have solar. In other cases, they might change rates. We also have the hourly changes in those specific tariffs. So if there's anything like some time sensitive rate that might change based on like hour, like a time of use rate, or even if it changes seasonally, that's reflected in the rate that we have. We also finally have, we distinguish between fixed and volumetric charges. So obviously solar can only impact the dollar per kilowatt hour portion of your bill and can't impact a sort of like minimum bill situation or fixed cost. So we do account for that. So again, we did have to make assumptions. This is zip level, but we did try to make it as specific and as true to what was actually going on in 2021 as we could. Finally, to come up with the ways that the solar system is paid back, again, we have empirical information on the cost and the incentives, but we don't know necessarily how, what terms they got. So we have empirical energy sage data, but it's not for the specific systems themselves. So what we had to do is basically look at the data, and then based on the solar system size, the state, and the year, we come up with assumptions based on those 3 things that we can then apply to the adopter. And this was sort of the area of the most uncertainty, and obviously it has huge importance to our results just because it's the cost part of the benefits versus costs in that numerator. So we actually did run sensitivities, and just all that's in the paper, but just to note that our results were robust to all the changes in both the lease and the loan terms. So as I mentioned, we're a bit bound by the data that we have because it is empirical, and this follows essentially the state of the residential rooftop solar market 2021 and before, and that is very dominated by California as a whole, and therefore our sample is also dominated by California as a whole. So I think that's important to keep in mind when I'm going over results that are for all of the adopters, and also especially in the regional portion where we talk about the West, obviously that will be even more so dominated by California. So quickly getting into results. The first bullet in the main takeaways was this statement. So solar decreased energy burden for the majority of adopters. Again, this is taking into account the cost. So in both A and B figures, you see that everything from 0 on to the right means that there was savings. So A is the percentage point burden reduction, and B is the dollar savings. So you can see it kind of peaks between 0 and 1 for energy burden point reduction, and it peaks somewhere between $500 and $1,000 in terms of annual savings. And that's what we saw here. So the average customer saw a 0.6 point reduction in energy burden, and that was about $700 annually. And this is also just a call out because, again, I just want to emphasize how important it is to take into account costs. But if the repayment essentially was ignored and only the bill impacts were considered, these values would be very inflated. So that 0.6 percentage point reduction would turn into a 1.7 percentage point reduction, and that $700 would turn into $2,000 of bill savings alone. So this is just a shout out to why it's so important to take into account both the cost and the savings. So as you can see here, the area to the left of 0 is not empty. There are some people who saw their costs exceed their benefits financially. And we did also in the paper, we did look into what this was correlated with to sort of figure out, what might be driving that. And this is in order of importance. So this happened more frequently for those with low electricity prices. So if you have a low dollar per kilowatt hour cost of electricity, then the bill savings that you see by producing your own, by generating your own electricity it's going to be a muted amount of bill savings. Next is more expensive per watt solar costs. That's pretty straightforward. It just means that the solar cost was higher. And then the third one was higher income. So for this, it could have been that some people adopt solar for reasons that are maybe not economic. If they just want to have solar on their rooftop and they don't mind paying a premium for that, that could also have been the case. So these are 4 of the groups. I'm not going over the year of adoption. That's the one grouping that is not in this presentation, but it is in the actual report itself. So again, you can see here that every bar except one is in the positive direction. And this just goes to show, again, that solar reduced energy burden across all groups, except for the South, which we'll get into for that specific slide in a moment. But I also wanted to note that the y-axes are all scaled the same. So you can also kind of compare magnitudes of the different percentage point reductions. So you can see here that, again, solar reduced energy burden for low income. So again, at or below 80% of area median income. They was able to do it more so for that group, more so than any other group on average. So getting into the specific groupings and walking through those 4. First, I wanted to focus on the income groupings. So here you can basically see that income grouping, but broken out a little bit more. So this figure shows low income, moderate income, and then non-lower moderate income. So again, that's at or below 80% AMI, 80 to 120, and then above 120. And then what you can see here again is on the far left of every grouping, that pale box is energy burden without solar. The far right box in every case is energy burden with solar. And then that middle one will be the bill impacts alone. So just the savings and none of the costs. So what we see here again is that solar was able to reduce the percentage point energy burden by a lot. And it's, again, more prevalent with the low income adopters in our sample. So here you see the median go from 7.7% to 6.2%. That is on average about $660 of annual savings. One thing to note is that while the percentage point decrease is largest for low income, just the way that the energy burden metric is structured, and there are pros and cons to the energy burden metric as a whole to sort of be a proxy for energy affordability. Again, we focused on it just because of its prevalence in a lot of these programmatic goals, and but again, there are pros and cons, and one is just the way it's structured is that if you have income on the denominator, then a lower income would mean that a smaller dollar change in the numerator would have a larger percentage point change as a whole. So it makes some sense that you see a larger percentage point decrease, but not as large of a dollar savings in low income versus like non-LMI, for example. So we also look at that dotted line, the dash line and the dotted line at 6 and 10% respectively to indicate those above sort of the cutoff for a high energy burden and a severe energy burden. And we see here again that solar not only reduced energy burden as a whole, but also reduced the incidence of high and severe energy burden. So just like the area inside the boxes, essentially. So for low income specifically, there were 66, so 2/3 of all of the low income adopters before solar had high or severe energy burdens. And that was reduced to 53% with solar. So you see that a pretty large drop in incidence from 66 to 53, which is fairly significant. Here for moderate income, you see again a pretty big decrease as well with the incidence. It's important to note that for this moderate income group, there were more customers that were sort of in that high energy burden space, but not really in the severe energy burden space like it was in the low income grouping. So basically what we see again is that second bullet from the main takeaways, which is that solar was able to reduce energy burden both in magnitude, but also in the incidence of high and severe energy burden. But it is really important to note that the incidence is still above 50%, specifically in that low income grouping. So what we have here is that solar reduces energy burden, but for some households, it reduces energy burden from a very high level to a still kind of a high level. So even though you have this big reduction, the end result might be still that the energy costs are burdensome for a household and difficult to pay. So this is really important to note. Again, my second call for why it's important to take costs into account is because if you were to erroneously kind of look at that middle bar, so just focusing on the low income group, just looking at that middle box, you would kind of say like, okay, just looking at bill savings alone, solar was able to decrease energy burden to below like that high level of 6% for 75% of low income adopters. Great. But in reality, again, once you factor in costs, you see that just over half are still above that 6% level. So this is really important to note. Solar is beneficial, and for those where it decreases the burden to a manageable level, it could actually sort of financially help the household. If you have access to friendly capital or third-party ownership, and you're able to pay back the system, it could improve your credit. It could obviously decrease your overall energy burden. So it could have huge financial impacts that are positive, and that's especially the case too we see that with the moderate income adopters. However, if you have a reduction of energy burden but still too high, there could be some financial impacts that might be negative to a household, especially in the case if you are unable to pay back the system. That could have some, obviously some impacts if you're not able to pay back your debt on stuff like credit. So I guess the main takeaway here is that solar is a great strategy for reducing energy burden, but we still need to be cognizant of the level that you end up at. And also it should be considered as a complementary strategy to things like bill assistance and weatherization in these specific cases. And also there could be more done to decrease the cost to make that sort of benefits to cost ratio even better for, again, I'm more speaking about the specific low income segment that start with a really, really high burden. So any incentives that would lower the cost. And then again, I guess theoretically, if you eliminate the cost, then you do see results that would look like that middle bar there of just the bill savings and no costs associated. Okay, so moving on to the ownership structure. So here we have, again, empirical information on if the system is host-owned or third-party owned. And so what we see here is that we don't see like a too huge of a difference between those with loans or leases. So 2/3 are host owned, and we assume that anything host owned is being paid back on a loan. And then 1/3 is third party owned, so we assume that that is a lease. And so here we see that lease systems have a slightly larger burden reduction, but I do want to caveat this with the fact that third party ownership or leased systems are more prevalent the lower the income for the household. And that is something we found in our annual solar demographics report. I linked it here as well. So some of these results might be conflated a bit with the income results. And I just wanted to state that up front. So that might be why you're seeing the leased systems starting at a higher energy burden and then seeing a larger point decrease. So that finding, this is the third bullet in the main takeaways, is that there was a lot of regional difference. Here, we broke it out again between low, moderate, and non-LMI. The bars are the same, so the boxes are without and with solar. And also just a quick note that the low income graph, the y-axis is scaled differently, just especially because of the range of the data points, especially in the Northeast. But just to reiterate what I mentioned earlier is that across all regions but the South, you see that solar reduced energy burden for adopters across the income groups. And again, the one exception is in the South where the very low cost of electricity made it so that the cost of solar adoption exceeded the bill savings. And you can see here that the Midwest and the South, you start out with pretty low energy burdens. So in just the low income graph, that top one, you can see the starting point of the Midwest and the South are way below that of the West, and then the Northeast is the highest at the starting point. So even with solar adoption, it does increase energy burden. So here you see it go from 5.8% to 6.9% for low income households in the South, and this was a $435 a year cost. So you do see it kind of toggle from below that 6% to above it, but it still actually ends up lower than some other regions, even with that cost increase. So that's one thing to keep in mind. In the West is actually kind of notable just because I mentioned earlier that in the low income groups, you saw a larger percentage point decrease in energy burden, more so than the other income groups, but not necessarily a larger dollar reduction in costs compared to the other groups. The West is that one exception. So actually, the West was the only region in which the dollar savings in the low income group exceeded those in the other income groups. So you see that the energy burden reduction was very high in the West, especially for the low income group. And this is shown here. So 7.3% for a median in the low income group went down to 5.7%, and that was $820 in annual savings. The Midwest, again, it starts from a low point. So energy burden is fairly low in the Midwest due to, again, just low prices. And you see that the energy burden went down, but again, not as much as in other areas. So 5.7 to 5.2 or $166 annually. But when you compare that to the low income group writ large, it is far lower, like in terms of savings, as some of the other low income households. Finally, in the Northeast, so the Northeast starts out with the highest energy burden, higher than any other region. And this is because of two things. One is that they have a high prevalence of heating degree days. But not only that is that they have non-electric heating, and especially they have some fuel oil and propane for heating fuels, and those are just way more expensive than electricity and natural gas. So here you see that solar led to a very large point decrease in the Northeast. So 8.8% to 7.6% for that low income group was $461 in savings. So that's a lot more than like the Midwest, for example. However, the sort of end point is still very high. And this is because, again, we just looked at solar. So we just looked at solar's impact on energy burden, which means that we only really looked at the decrease of the electricity burden. And solar was obviously not able to impact any of the non-electric burden part of that calculation. So it didn't impact the natural gas, the fuel oil, or the propane burden of that household. And this brings me to the last result slide. So customers with propane and fuel oil have much higher energy burdens. Again, this fuel is way more expensive than electricity and natural gas. And also it is basically only in the Northeast where you're using it. There's a large number of heating degree days. So I think the one thing I also want to note is that I haven't focused on the non-LMI portion of the income groups that much in this presentation, but I did want to note that of the very small group of non-LMI solar households that had sort of burdens exceeding 6%, essentially all of them are just ones with propane or fuel oil as a primary heating fuel. So that is a very large driver of the energy costs across income groups. And so then it might make sense that of all of the low income solar households with propane or fuel oil, 85 and 80% respectively maintained energy burden levels higher than that 6%, even with solar. So this again is just to reemphasize that solar on its own can really only impact electricity burden. So there are other things that would alleviate some of these high bills. So bill assistance is obviously one that kind of decreases energy burden regardless of household, and even like gets over the tenant versus homeowner issue. Weatherization just basically reduces all heating and cooling load. So that would reduce burden of whatever you're using for heating. So any sort of heating fuel you'll need less of and therefore have a lower cost. And then also in cases of propane and fuel oil especially, it might make sense to sort of apply some selective electrification or something to basically, if you were to pair solar with some other programs or something to basically shift that load into electricity load, and then solar could, take care of that cost of the heating cost more so. But again, that is sort of out of the scope of this paper, and a lot more work would have to be done to sort of investigate the financial impacts of doing that. So with that, we're back at the first slide, hopefully with more of an understanding of the work. So again, just to run through quickly, solar adoption was able to reduce energy burden for 3/4 of adopters, and that is taking into account the costs. Solar reduced burden, especially for low and moderate income adopters on a percentage point basis. But while this strategy sort of works maybe well on its own for moderate income adopters, slightly over half of low income adopters maintain an energy burden just above 6%. So it is important to sort of, in these cases, consider solar as a complementary intervention that would pair well with other strategies that exist, like weatherization and bill assistance. I suppose that's true, honestly, for any income level, but especially important for this group where if they do have a host-owned system or something, just to make sure that they're able to pay back the system and sort of get those financial benefits and maybe credit benefits of paying back the system without it still being a stressful amount of energy burden. And then I talked pretty extensively about the results by region, but the upshot here is that the regional stuff honestly reflects some of the other results. So the Northeast has a lot of non-electric heating and a large amount of heating degree days. So that had a big impact. The South has very low electricity prices, so that had a big impact. And then again, this is kind of like the accumulation of all of those other results. And with that, I think Eric has been manning the Q&A, and I have Eric and Chris on the line, who both were co-authors on this to join for Q&A. And this is a link to the open access article and the report page where this presentation will be posted afterwards. And then if you're curious about more work from our department, that's the second QR code. So I appreciate all of your time.
Great. Well done, Sydney. There are lots of questions here. I'm going to start with a sort of rapid fire of related questions. And in some cases, as always happens in these webinars, we dump a lot of information. So you might have covered some of these, so maybe they're clarified. So let's start with 3 related about what the costs account for, what costs are accounted for in the analysis. And the 3 are, do we account for outright purchase costs, some sort of net present value? Do we account for tax credits? And do we account for price appreciation of the asset, which I'm going to take as, do we account for how the value of the asset changes over time, which is likely a depreciation because solar systems tend to depreciate rather than appreciate over time.
Sure. So the costs all came from tracking the sun. So this is basically the cost that the customer is paying for that includes everything. So anything that a solar developer would charge you for is included. I think this could even include like if you needed roof repairs. So just all in. It also does include, we have empirical data on any sort of incentive they received. So if you received some sort of dollar per watt incentive from a state program, if you have some sort of production credit, all of that is also applied. So that's everything in tracking the sun. Tracking the sun does not account for federal or state ITC, and it doesn't account for the solar renewable energy credits. So we applied those separately based on presence of that incentive, eligibility for that incentive, and also, again, like what was available at the specific time and location that solar was installed. What was the other question? We do deteriorate the panels from the year that they were adopted. I think it's 0.5% per year. We also do apply some shading and soiling depreciation. So when we're talking about the bill savings, we do have like an altered kilowatt hour per hour than what is just spit out by NREL's SAM model. Was there another question there that I didn't answer?
No, and then I think 2 related ones are, do we account for end of life costs? And just in general, do we account for, there's one question about the difference between manufacturers and product quality. So just any sort of differences in model performance, I think is the gist of the questions.
Oh, okay. No, so the capacity factor was based on NREL's SAM. The end of life, actually, this is maybe just a question. I don't know, Eric or Chris, like if you install solar on your roof, is that included in the purchase price? Because if yes, then yes, we account for it. If no, then we don't, is the honest answer. But I just don't know if that is included usually.
In a lease, certainly, with a purchase,
Okay.
it would depend on the contract, but it's not going to be a sizable chunk of the. I think just the overall point is that solar at any scale, the vast majority of the expense is upfront unless you're financing. So I think that we're capturing all of the major costs in there. There's a couple of questions about storage. Does the analysis consider anything about solar and storage?
We do. I think some of the systems do have energy storage, but we don't necessarily break it out that way. again, this was in 2021. We're seeing higher attachment rates of storage with residential solar more and more every year. And that we do have in our solar demographics report. However, we just didn't have count numbers high enough to really include if we wanted geographic coverage across the US, because a lot of that has been concentrated in very specific areas.
Great. There's some questions about data. I'm going to say the study uses a lot of different data. So for the specifics of the data, I just refer everyone to the study. But I think this question of how reliable is the data just in general that we drew on. And you mentioned some of this, but I'll give you another chance to reiterate.
How reliable is the data? The tracking the sun data is from the source, so it's as reliable as you're going to get. So all of that empirical solar system data is very reliable. We do some sense checks because obviously in any big data set, you'll get some weird nonsensical values of people maybe entering it wrong. So we do filter out some of those weird bits. When it comes to the income information, I mentioned that this was an Experian model. That is something that I think we struggle with knowing how accurate it is. We've done a few kind of side studies that show that like on aggregate, so for something like for 500,000 customers, it is pretty accurate. But when it comes to like how did it nail that specific household's income, it will be different. It is an estimate. The areas of the most uncertainty, we made sure to run sensitivities on. So like that energy sage data, we got a range. Obviously, we don't know the loan terms. We don't know the credit score of the household. So we don't know exactly what they got. But in those cases where we thought that it was more unreliable, we did sensitivities on kind of like the range there. And we ran like a Monte Carlo and everything. So there were areas where there was more uncertainty, but we kind of tried to cover our bases by then treating it as a sensitivity. Again, the tariff data is empirical, very reliable. Some of the stuff too, like the non-electric costs are very reliable, but they're aggregated. So whether or not they're reliable to that specific household again is not necessarily the case just because it was aggregated at a regional level. But yeah, so we did a ton of work to combine everything. You can see the report for how much work it was just to sort of compile this data set and make everything agree. But yeah, like with anything, there are some uncertainties. Things like calibrating the modeled load data also to fit was also a challenge. So there's definitely some assumptions and limitations in this.
As the saying goes, all models are wrong. Berkeley Lab models are useful.
I didn't know
So,
that was a saying. That's
oh,
cool.
it's totally famous. All right. Did the modeling of your low-income customers include customers of subsidized programs like in Grid Alternatives, so like California SASH? And then interesting on if for customers that receive their system essentially free of cost, are the impacts more akin to the electric bill savings only graphs?
Yeah, great question. Yes, to both. So the low income, we actually have empirical data on low income incentives received. And so we also like know which systems again are like grid alternative systems. That's all in there. We couldn't like separate that out again just because of count numbers. It would be really hard to like say anything with significance with a smaller group like that. But and there are some systems that were installed at very low or even zero cost, and those would look like the middle bar in that case, so that the just bill savings alone. So that's absolutely true.
Great. We did not do this in this study, but someone's curious about your thoughts. So it'd be interesting to compare rooftop solar energy burn impacts to community solar energy burn impacts. So would you like to speculate on any potential differences?
It depends how it's structured. So I will say that there are some community solar programs where you have to pay a premium. So obviously, if you're paying a premium, the cost is higher. And there are some that are structured such that you're guaranteed a certain amount of savings, and they might have flexible subscription terms, so you can back out without penalty if the savings aren't appearing. So I think that like it's it's maybe similar to if you have a leased system, you have they're usually structured to be a certain percentage off of your retail sales, but even better because again, you're not locked in for decades. So I don't know, Chris and Eric, do you have speculation?
Well, I was gonna let Chris go, but yes, community solar 100% is going to be more similar to leasing. It's generally no upfront costs. Oftentimes, community solar programs are designed to be bill savings, sometimes by law, and sometimes targeted bill savings towards low-income customers. So it's not a totally fair comparison. But yeah, I think that is an interesting question, and maybe it's something we can uh, look towards in the future. So maybe that's a good segue to one question about what are the next steps for this type of study. You mentioned energy efficiency results, and I know that you are working on some next steps, so maybe we can talk about those.
Yeah, and not just myself, but some of our other colleagues. So we're working with some researchers who did survey work. So I mentioned that energy burden has some pros and cons. I think that one big con is just that it doesn't necessarily account for if a household is rationing their energy use to reduce their bill, but keeping their homes at uncomfortable or unsafe temperatures. It also doesn't necessarily capture the more qualitative experience of energy affordability. So there is a paper in review that did a bunch of survey work. So it's kind of like the qualitative sister to this quantitative study. So that's one. The second is just that we are doing work, and it's a bit more simple because it's using all open access data, so stuff that's publicly available, to look at solar's complementary role with bill assistance and weatherization. So it's looking at a programmatic level, like what makes sense to invest in, because there's, again, trade-offs with each. Bill assistance is immediate. It doesn't care if you're a renter. And it directly reduces energy burden. However, it doesn't really address the underlying issue. Energy efficiency is usually way cheaper than stuff like solar, but again, there are limitations to how much you can weatherize a home and achieve savings. So a lot of these are kind of low-hanging fruit, and it gets more expensive to go deeper, and then all of a sudden, like the payback rate can change, et cetera. Solar is way more upfront, but again, it doesn't impact things like non-electric burden, like energy efficiency can, but it lasts a long time and is also direct bill savings. So I think that all three have a place, and sort of putting them all together is the next step for us specifically. Beyond that, I think that there's more work that could be done with like someone asked a question about like stuff like community solar we don't cover. I also think, like I mentioned, we don't get into any sort of fuel switching, electrification, any of that. So that would be an avenue for more exploration. I don't know. Again, Eric and Chris, do you think of anything else that might be good for future research?
I guess maybe something that I would add is that in this complementary paper that we're working on that looks at energy efficiency and bill assistance, since we are using fully public data, I think the methods that we craft up there and will make publicly available could be easily used to explore these other technologies such as fuel switching or storage that others mentioned, to think through energy burden reductions in electricity intensive pathways, or those actions that help in non-electrified scenarios like energy efficiency that Cindy was mentioning. So hopefully you'll also be interested in that second paper that uses data that is more public, and hence those methods can be easily replicated and taken further by others too.
Great. There are two questions about the regional results. One is just, I think, more of a clarification. Maybe you can go back to that slide. The boxes on the regional results are only bill impacts, or do they include costs as well? And then maybe the bigger question is just curious why the South bucks the general trend.
Yeah, so all of the figures just show the costs included if there's only two bars. So really at the beginning, I only put the bill impacts only just to emphasize why it's important to consider the costs. And then I sort of like, okay, made that point, shoved it down everyone's throat so many times that now we can just focus on the energy burden with and without solar, inclusive of cost incentives, et cetera. In the South, I don't remember off the top of my head, it's in the report, but we do show like the average prices of electricity. Again, the tariff is specific to the zip code. So this is averaging across all of the hours, which also differ, and all of the households in whatever region it is. But the electricity price in the South is very low. And again, we're talking about net metering. So the savings for the bill is that retail rate in the South, and it's just very low. So that basically values the solar at the price of that low rate. So the cost might be similar to other places, but the value is lower in the South. So that's why we see the lower savings and therefore increased burden.
Maybe, yeah, Chris is going to knock out some of these other questions. There's some just ideas here, but continuing this regional question, what rates did you use for the West? The West in quotation marks is a huge area, so we just like define that. The data broken down by utility, used for PG&E.
Yep, zip level
Yeah,
that are specific to the hour. So, and it's also their actual tariffs in 2021.
and maybe just so rates have increased. So just general comment on like what the implications of rate changes might be.
Oh, that's a good question. That's an area of exploration as well. This was 2021. Not only have rates increased, but they've changed in structure temporally. So I think that's really important to note. So when you go from a flat rate to a time of use rate, that's very important. If the sort of peak is coincident with solar production, that will improve your bill savings. If the peak is not coincident with solar production, so it's in the evening or the evening hours, that will hurt your energy burden reduction potential. And then more than that is the migration from net metering to other things like net billing. So if your exports, so your excess solar generation is being compensated at lower levels, again, that will impact your bill savings and therefore your energy burden reduction potential. So like if the net exports are valued at half of what the imports are, that has a huge impact. So, not only are rates increasing, which again, if you just take that alone, so you say, okay, I have a flat rate net metering and the rates are increasing, that for sure improves your solar benefits, your bill savings. Some of these earlier TOU rates in areas where solar penetration is lower, that probably also helps your energy burden reduction potential because you'll see the peak coincident with solar. But in places, again, like California, where they're setting the peaks to be after solar generation or they're valuing exports way lower, then without things like demand response or batteries, it would be hard to sort of capture all of that, and then the savings will decrease. Again, the West is in 2021 saw the highest level of energy burn reduction. So I don't know like to what extent that would erode, or increase in areas like the Midwest that are sort of taking on time of use rates. That probably help.
Great. Well, those are really good questions. I will give you the last word and let you close this out, Sydney.
Yeah. I am looking, can you guys see me?
Yep, you're still there.
Okay. My computer's been behaving a little bit weird this this session, but I think you can still see my screen. Eric is co-host, and I think that that's a sign that we are done for the day. So I appreciate all of your guys' time and joining, and this will be made available on that, with the QR code, or if you just Google this and LBL, it should show up. And yeah, I appreciate everyone's time, and please feel free to reach out if you have any questions.
Great. Thanks, everybody.
Thank you.